now let's talk about nuclear fission. So fission, like we said in our previous class, is a splitting. So when there's a splitting of heavy nuclei, it gives us nuclear fission. I'm going to give you an example. If you have a uranium nucleus, it is uranium 23592. If we say uranium nucleus is bombarded by a slow moving neutron, so we bombard it with a slow moving neutron. Bombarding simply means you are adding to it a neutron, and then we now have a result which is uranium 235 plus 1, 236, 92 plus 0, 92. So if we are told that the uranium nucleus is bombarded by a slow moving neutron, and then the nucleus splits into two medium mass nuclei with the release of huge amounts of energy. The reaction can be given as follows. So if you bombard it with this, and then it splits, so it could possibly form barium 141 with this is plus krypton. If we notice, when we add this plus this, it gives us 92. So it seems to be balanced. But if you add 141 to 92 here as the mass number, we're going to have 233. There's a missing of, is looking for, it needs 3 to be complete. So I can have a neutron there, but 3 of the neutron. And then, of course, my energy is going to be released. Energy is going to be released in this whole equation. So it's going to be plus energy released. And as we go on, I'm going to calculate the energy in these different cases. So this is for a sample nuclear fission. Then what happens on nuclear fusion? Nuclear fusion, like we said in the previous class, is when two light nuclei, is a process of combining two light nuclei to form heavy nucleus with the release of huge amount of energy due to mass defect. So light plus light to form heavy. That is nuclear fusion. So when two light nuclei are combined to form a heavy nucleus, the mass of the product nucleus is slightly less than the sum of the masses of the light nuclei fusing together. As a result, there occurs a mass defect in nuclear fusion. This mass defect results in the release of very large amount of energy, like we have said, and you can get that energy using what? The Einstein's equation, which is changing E equals to changing N times C. So now we're going to go further to understand how we can calculate this energy. In order for us to be able to calculate this energy, sometimes in some cases they will give you the mass of the several elements involved. But let's take note of this. The following masses: mass of deuterium. Mass of deuterium is 2.014102. So in this case, yes, not like for decimal place, you have to use all U. Remember your U, atomic mass unit. So mass of, this is 1, this is 2, mass of hydrogen. I want you to take note of this as we go on. So the mass of deuterium is that, mass of hydrogen is that, mass of helium, mass of tritium, mass of electron, and the mass of neutron. I want to note this because in our next class, we're going to use them to solve. We will not need to be writing them out as we state the questions. Okay, so now we are going to take some examples. I will calculate the energy release, find the energy release in the nuclear reaction below. So we have tritium, adding to deuterium. Remember we said there are isotopes of hydrogen, tritium plus deuterium. Then we have the helium, nuclear, and neutron. The energy released. So we're going to look for this energy that is released. 3 plus 2 gives us 5. 4 plus 1 gives us 5. It's balanced. 1 plus 1 is 2. 2 plus 0 is 2. It's balanced. Now, what is the energy released? How do we find such? So we said we are going to look for the masses on the left hand side, and then we'll look for the masses on the right hand side. Before now, we had said in our previous class that tritium has a mass. That mass is 3.016049. Then we add it to deuterium 2.014102. When you add it, you're going to have 5.030151. Then for the product, we have helium. Helium is 4.002602. You have neutron, which is 1.008665. When you add it, you're going to have 5.011267. Remember we said that the energy released, or the binding energy, is energy required to split the nucleus of an atom. And then that binding energy is actually the mass difference of the nucleus and nucleon. So that energy is the difference between two of them. If you look at them, which one seems to be bigger? This is bigger. So we'll subtract. We're going to subtract them and find out what their difference is. So 5.030151 minus 5.011267. When you subtract, you're going to have 0.018884. What's atomic mass units? So this is the binding energy. That's the difference between them. Then it could be in atomic mass units, or we have to convert to mega electron volts. So how do we do such? We need to convert this to mega electron volts. Remember, we said 1 mega electron volt is 1 mega electron volt. Sorry, not 1 mega electron volt. 1 unified atomic mass unit. 1 unified atomic mass unit is 931 mega electron volts. So if you have one of these units is this. So this will be how many? Just simply basic mathematics. If 1 unified atomic mass unit is this, then 0.018884 atomic mass unit will be what? Unknown. And then when you cross multiply, you see that x multiply 1, which is x, then this times this will give us our result. So this will be the 0.018884 times 931. And you multiply that now, we're going to have 17.6 mega electron volts. So basically now, based on this, every time you want to convert from unified and atomic mass unit to mega electron volt, you just multiply by 931. That's the energy released, which is this energy. Yeah, that's how we calculate the energy released. Just get their masses here, get the masses of the product and the reactant, the product, and then subtract them. When you subtract them, you get the difference. That difference is the binding energy. Convert it to mega electron volts, you have this. Of course, we can still convert it to joules. You multiply 17.6 by 10 raised power 6, which is mega, then 1.6 times 10 to the minus 9. When you do that, you get your answer in joules. So let's try it. So 17.6 mega electron volts will be 17.6 times 10 raised to power 6 times 1.6 times 10 raised to power minus 19. So what is going to be our result? So we're going to do the 17.6 times. So after multiplying, we're going to have 2.8 times 10 raised to power. What I got is 28.6 times 10 raised to power minus 13. So then we'll go back times 10 raised to power minus 12 joules. So I just showed you something that the energy released in this situation is what? 0.01884 unified atomic mass unit. But then in mega electron volt it is 17.6 mega electron volt. In joules it is this. So you have to know how to convert each of them. From unified atomic mass unit to mega electron volt, you multiply by 931. Then from mega electron volts to joules, multiplied by the possible by 10 raised to power 6 and 1.6 times 10 raised to power minus 19. So this is how we calculate for the nuclear energy release. Thank you.